Chapter 7, Atmospheric Pressure and Wind, Naming Global Circulation Important Features. So let's look at the three-cell model that we developed in Chapter 7, and let me help you recognize the various features in this model that are important to this course. The first feature that we should recognize is a band of low-pressure systems that exists at and near the equator. This band of lows moves with the tilt of the Earth. It moves a little bit higher into the northern hemisphere in the summer months of June, July, and August, and moves below the equator into the southern hemisphere during December, January, and February. So this band of lows, we call it the intertropical convergence zone. It's the meeting of the northeast trades and the southeast trades either side of it, with the northeast trades being in the northern hemisphere, the southeast trades being in the southern hemisphere. Now the band of lows at the intertropical convergence zone also represent thermal heating, so convergence and thermal heating convection. And if you look at the side profile, we can see the air moves into the intertropical convergence zone from higher latitudes, and then it moves up into the troposphere till it reaches the top of the troposphere, and then it moves poleward. The next feature that we should take note of in this global circulation model is a band of high pressure centers that exists at about 30 degrees north and 30 degrees south. The official name for this is the subtropical high pressure zone. Once again, this zone moves up and down depending upon the seasons, and it is an area of descending air, high pressure, clear skies, and it produces two winds. Equatorward, we have the trade winds, the northeast and southeast trades, depending upon what hemisphere you're in, and it also produces the westerlies, which occur between 30 and roughly 60 degrees of latitude, both in the northern and southern hemisphere. As I said, the subtropical high pressure zone is an area of descending air, and this is air that was originally uplifted at the intertropical convergence zone. And if you look at the side profile, you can see that the downward movement of air, and then it moving outward from its surface location, producing the westerlies, and as I said, the trade winds, northeast in the northern hemisphere, southeast in the southern hemisphere. Another band of pressure that exists in our global model of low pressure are the polar lows, and the polar lows have roughly they occur at a latitude of roughly about 50 to 60 degrees north and south of the equator. They consist of air moving upward. That's what produces the lows, and those lows aren't generated thermally. They're generated by circulation. So you can see that the air coming down from the high pressure zones that exist at both poles, it collides with subtropical air that was moving from the subtropical high pressure zones. So this collision is what creates the uplift, and what's uplifted is warm air over cold air, producing, as I said, this band of low pressure systems. In the northern hemisphere, the band isn't continuous, and we notice there's two areas of low, one over the Aleutian Islands and one over Iceland, Greenland, tip of Greenland. In the southern hemisphere, it does appear as a band of lows, and those lows are completely around Antarctica. Okay, so let's name our winds again. So the winds being generated from the subtropical highs in the north and southern hemisphere, and produce through convergence, help produce the intertropical convergence zone. These are the trade winds. So the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The winds generated by the subtropical highs moving poleward are called the westerlies, and they have the same name both in the northern and southern hemisphere. And that air collides with air descending from the two poles, and those winds that collide with the westerlies are called the polar easterlies. And what happens along that low pressure zone at the polar lows is the warm air is pushed up, cold air is pushed down, and those lows produce mid-latitude cyclones. So those lows represent areas where mid-latitude cyclones are forming and moving across from west to east. Let's now name the various circulation cells. So in this we have a 3-cell model, 3 cells per hemisphere, and those cells are generated because of Coriolis effect. So if we follow the Hadley cell, we have air moving from 30 degrees north and 30 degrees south towards the intertropical convergence zone. At the intertropical convergence zone, those two winds collide, so you get convergence. And at the same time, you've got thermal heating, which is creating convection. The air moves up to the top of the troposphere, and then it has to go somewhere, so it moves poleward in both the northern and the southern hemisphere. Now, because the air is being deflected to the right in the northern hemisphere and to the left in the southern hemisphere because of Coriolis effect, that air ends up moving not poleward, but along that particular line of latitude at about 30 degrees south and 30 degrees north. And that air just can't keep building up. Some of it has to move down. Some of it creates the subtropical jet stream, and some of it continues on its journey at the top of the troposphere, producing the top flow of the next cell, which is called the Ferrel cell. So the Hadley cell is from the equator to about 30 degrees north and 30 degrees south. The Ferrel cell is the second cell, and it's occupying a region between 30 and 60 degrees north and south. Notice that the flows at the surface and at the upper atmosphere are in the same direction, poleward. This cell is not a typical cell in that it's got enclosed a circulation pattern. It has these winds at the surface and the upper atmosphere moving in the same direction. And those upper air winds are called upper air westerlies, both for the Hadley cell and the Ferrel cell and even the polar cell. Some of the air that's moving in the upper part of the Ferrel cell descends, cold flows usually that occur behind mid-latitude cyclones. Some of it continues its flow into the next cell, which is called the polar cell. At the Earth's surface, the Ferrel cell produces the westerlies, and at the poleward end of the Ferrel cell, we have the polar lows. For pressure, surface pressure, at the beginning or the beginning of the Ferrel cells, we have the subtropical high pressure zones. The top cells are called the polar cells, and they consist of an upper air flow that is moving poleward and surface flow that is moving towards the equator. And the high pressure zone occurs at both poles. The descending air in that high pressure zone is called the polar vortex. And so the polar cell consists of high pressure at the poles, and at the bottom of the cell we have the polar lows. And that cold air meets with the warm air in the Ferrel cell at the Earth's surface. We have two sets of jet streams, and these jet streams are caused by Coriolis effect, moving upper air winds, not poleward, but parallel to the lines of latitude, and that occurs at about 30 degrees north and south and at about 60 degrees north and south. The jet stream at roughly 60 degrees north and south is called the polar jet stream. And it's a very important jet stream because it plays a role in the generation of mid-latitude cyclones. The jet stream at 30 degrees north and south is the subtropical jet stream. And once again, it's created because the winds in the upper atmosphere are being deflected to the right in the northern hemisphere, to the south, or to the left in the southern hemisphere. And that creates a ribbon of air that's not moving poleward, but moving parallel to the line of latitude, which is roughly 30 degrees north and 30 degrees south.